Hello everyone. In this video, I'm going to show you a demo project to use Xilinx high-level synthesis tool. The HLS tool is focused on helping software people to convert C or C++ sources to HDL files so that the functions that originally developed from the software perspective can be easily combined into FPGA projects. So is this HLS workflow really useful and efficient? We will find out in this video. Now let's start. To demo some calculation-intensive software code, let's try the SHA256 hash function. It's a standard calculation and quite a bit of steps to do it. You can probably find the source code on internet. So I just asked ChatGPT to show me some demo codes. Here is the code she showed me. As you can see, it's very simple steps that use OpenSSL library. We can put this into high-level synthesis, see how it goes. We can create a new project. Just give a name. We will add this file here. And specify the main as the main function, entry point. We will also demo the project later in the KingTest evaluation board, see how it goes. So we just select the KingTest board. As the part selection. The target will be just use Vivado IP flow, so it creates a whole bunch of HDL files. So the source file is set in the project. You can take a look, see. There may be a problem of using the OpenSSL library. We can see if we can go through. So there is an error saying OpenSSL library is not there. So we cannot just use the library. All these steps are actually purely calculation of bit mapping, so pretty sure we can just use a pure C file to create these steps. I will ask ChatGPT to give me a full file without the OpenSSL library. So there it is. Without the OpenSSL library, and the calculations, basically some SHA256 transform, initialization, update, final. So the main, just call all those steps. For the demo purpose, I'm going to generate the HDL file and put in the hardware, so I'm going to remove all the print that ChatGPT showed me. Actually, this file can be printed on screen, but on the hardware, we are just evaluating the memory bytes inside the project. So I remove the print, and I also change the initialization stream, the input stream for calculating the hash, to something specific, because later on we will also compare the pure HDL file I create earlier and see the difference between the pure HDL and the HLS generate HDL, the difference between them. So we can change the file in the project. Use this one. So there's no more warning. So we can convert this file. There's some warnings, but it does go through, so we'll see what's going on later. As said, the hash function is quite intensive calculation and use lots of bits, so there may be some memory mapping issues. Now it's done, and the report saying use quite a bit of flip-flop and nuts. In the folder, HLS generates some solution, and there is synthesized implementation, a whole bunch of Verilog files, also HDL up to you to use. So Verilog files looks like the main is the top file, and as you can see, basically the HLS tool just mapping all the C files into lots of finished state machine steps. For example, the main has 86 steps. The other transform function has 32 steps. The philo function is quite a bit, has 216 steps. So in the main, just like the function here, in the main it calls initialization and call the update and call the philo. Both the update and philo will call the transform. So it's quite structured, mapping to the HDL file. So we can create a simulation project and see how these HDL files go. Now we can create a simulation project. We will also use the king test as device. Now we add those files in the project. The text bench and the HLS generates solution. So in the text bench, we generate a clock reset and call the main function from the HLS generated HDL file, and start the app at the point and see how it goes. We will run the simulation for 50 microseconds. See if it can calculate the hash. Now the app is done around here, 48 microseconds. And there's no output from the main function of the hash. We have to go into the memory to exercise, see what the hash is. Looks like some memory is not initialized. So there's a main ROM, CTX RAM, hash RAM. In the main ROM, it reads the data, so this data file maybe need to put in the project. As you can see, the DAT file is not one of the support memory file. So usually it will be MEM or ELF or MIF files. So we can take a look what's difference between. The .dat file that HLS generates is our initialized input string, A, B, C, D, and the space, and looks like a text form. So it's very much like the MEM file, just without the initial address byte specified. We can modify this. And we don't need the ending byte. Now we can add this memory in the project, and we also specify this as MEM file. For the other RAM, there is no initialization, so we just need to add some initialization here. Other than reading the memory, we just set it to 0. And the hash RAM also doesn't have the initialization, so we just use the same thing here. Now let's run again. So it does generate something. Around 48 microseconds. Is this correct hash? We can verify that from Windows command line. So for that purpose, I put the input string in the file so that we can call Windows function. This is the binary of the input string, basically same. In the Windows, we can call the so Windows generates this 60F55A 77B2 60F55A 77B2, pretty much the same, so believe this is the correct hash. The remaining question is, how is this function that HLS generate, how many resources it needs to create this function, and compared to the pure HDL, does it faster or slower, or takes less or more resources? We'll take a look. So for that purpose, we'll bring in a bare metal KC705 project that pretty much has nothing other than just clock inputs and measurement of the clocks. Just measure the frequency of the clock and dump into a chip scope without anything. For the evaluation purpose, we will modify the top file and include those main features from the HLS generated, and also include the pure HDL function I created earlier. We can compare them side by side. So as you can see, I include the HLS generate function here, the main function, and the HDL pure HDL function here. Once the hash has been calculated from the main or from the HDL, we then capture the result and compare in the text file, which basically create a trigger to trigger the hash to generate, and then capture the result, also capture the timer count, see which one is faster. Trigger the match, see which one is faster, and the count difference between them. We'll see how this go. Generate a bit stream. So for compare purpose, I also add the output of the main feature. I also add the hash output direct from the memory module. So in the memory module, I add this output directly mapping to the RAM and passing through all the modules get to the main output, so that I can compare the hash with the HDL function. So there's an implementation problem. We'll see what's the error. It says multiple driver drive the same thing. One is register 0 on the hash RAM. Okay, as you can see, the two blocks setting the RAM with different addresses. So if we go back to the simulation, we can see that the RJS1 and RJS0, so the HLS generated block use two RJS buses and write to different memory, so 004AC, 1014, 1A, 1C, 59, so they're all different. So the two are ping pong, but in the real HDL world, that doesn't work. You cannot map to the same register in different block. We have to modify that into two memory blocks. Let's change that. So we'll change this to two different blocks. And I also reset the memory for the beginning. So the two memory, at the point we output, we just all them together. As you can see on the simulation, there's no overlap, so should be okay. Now let's do again. Now the bitstream is done. We'll see how many resources compare to each other. It takes quite a bit of flip-flop or locks in the king text. So here is the main functions: reset, checking the clock frequency, chip scope. That's the main from HLS generated code. That's the main of the pure HDL and the text function. So let's see. Highlight as yellow, this one highlight as purple, this one highlight as green. And on the device, wow, look at that. So this is the pure HDL. Those are the HLS generated code. Compares. That's just pure debugging purpose, so it doesn't really matter. But compare the resources here. This is the HDL. This is the pure HDL. This is the HLS generated code. Now we will download the bitstream to the real board and compare the performance, see how fast the pure HDL generate the hash and the HLS generated code converted from C, how fast it can generate a hash. So we will add the memory device. So the program is done. We reboot that. So as you can see, it reports CC, meaning matched, and SH0 is later. SH0 is the HLS generated code. The difference is 11CF. 45 microsecond. For 100 meg clock is 45 microseconds. So we can also look at the chip scope here. The value generates 60F577B2, same as before, and so if we trigger at the trigger rise, we see from the trigger to the pure HDL generate the hash only takes 69 clock, which is less than 1 microsecond. And for the final result, the difference 45 microsecond is pretty much match what the simulation shows. So the final verdict, the HLS tool can easily convert the C program to HDL file. There's some manual tweaking is necessary to combine the file in a real FPGA project. And also the HLS code does take quite a bit of resources. As you can see, it's doing very much the same thing, but in a pipeline fashion, so it takes very fast and less resources without using a lot of finished state machine. You can find all the codes in my GitHub folder. So that's it for today's demo. Hope you like the video. See you next time.